Okay. Remember in the last class we start studying vector field in 2 dimension, in 3 dimension, it doesn't matter. But this is a little bit crazy because the vector field is a bunch of vectors associated with any point, maybe in the plane or the space. So how you analyze this? This is complicated, very complicated. No, it's not complicated because today we study how we analyze the local property. What mean local property? One is in one specific point. Okay, we mentally try to do a circle, a small infinitesimal circle, and you study the property for any point separately, right? So to do this job, we study two operators. The name of this operator is curve and divergency. So now, what definition of this in operator? Well, operator, operator is something that you apply in the function and you get another function. So there are many examples of the operator. For example, differentiation, integration is operator. Right? So this is a new operator, divergency and curve. Let me explain divergency first. So the symbolic way to indicate, so suppose that we have a vector field. Okay, in 2D, we studied 2D first. Now 2D first. After I promulgate, I studied 3D. Now it's formed by two functions. Normally we call P and Q. P and Q are functions of the x comma y. No? So you can indicate like that. P x comma y, Q x comma y. But no, it's okay. I call PQ, it's okay. Now a divergency, you indicate like that. Divergency of the vector field F is equal partial derivative P with respect to x plus partial derivative Q with respect to y. This is definition. Now interpretation is another thing. Okay, the interpretation of divergency is relatively easy to understand because when the divergency is positive, when the divergency is positive number, it's a function, no? But when it's a positive, it's because we have source. I want to explain what means source right now. When the divergency is negative, is sink. And when the divergency is 0, is source free. Okay, let me try to explain this in more clear language. Suppose now, okay, we have, look, let me try to do my best skill drawing something. This is the bath tube. This is the, a false. And put a word like that. And here we have a drain. Okay, and see, I go, for example, I do, for example, the floor plan for this bathtub. I saw again this point is the point of the false. We have something like that. It's a water, right? In this direction, and it's a source. And the water flow in that direction. I go to the drain, and the water go in this direction. And this is the sink. Do you understand very well this or no? Okay, this is the idea for the divergence. I indicate, not only, okay, this was a funny example to illustrate sourcing. For example, here in the middle, in the middle here, this is a water flow in that direction. So you are doing, for example, a local property here, local property. You see that the divergence is 0 because the amount of water can get inside this surface is equal the amount of water can get out the surface. We have no source, we have no sink. Okay, entonces en few words, the divergency measures the net flow out at the point, at the specific point. And this is important, extremely important. See, we have source, a positive, we have sink and negative. And see, I visualize this in electric field. In electric field, we have positive charge and negative charge. It's exactly the same phenomenon. Okay, the electric line field travel from the positive charge to negative charge. And negative charge behave like a sink, and positive charge behave like a source. Exactly the same. Okay, this is important to understand. Do you get the idea for the divergency? This is definition. This is the formula. I promise we are doing today several examples to understand the idea, and you see in one animation I have prepared for you this idea when the source, when the sink, or when this source free. Everyone understand this so far? Answer me. It's clear? Divergence operator can help me to understand somehow the net flow out the specific point. We have yes or no. Answer me. Yes or no. Do you understand? You don't understand? I try to explain. Good. Victoria. Okay. Now, the next is a curve. The next operator does a bigger magnitude mean more line. See, for example, this is a good idea. See, divergence is equal to 200. We have more line, of course. More water. The divergence is just 20, entonces less than. Makes sense, yeah. So give me information about the source. So more flow, more divergency. When it's positive, it's source. When it's negative, is a sink. And when it's 0, no. We have no. Okay, remember this is a specific in one point. This is a specific one point. Okay, you are doing one little circle to analyze the flow. The flow get in and the flow get out. Okay, this is the divergence. Now we study a curve. A curve of the vector curve L. A curve of the vector field. CURL. Vector field. Definition is qx partial derivative q with respect to x minus partial derivative p with respect to y. It's a definition, a little bit different. And the meaning is totally different. Totally different. In this case, give me the information that the curve measure the control clockwise rotation of the vector field at the point, at the specific point that you compute the curve. Now remember, this property are local, so it's for the one point. You determine if the one point rotate or no. Now you can see, for example, when the curve of the vector field is positive. Okay, so now I suppose that the vector field in this point rotate counterclockwise. And the way to see in the animation, in the real life, the curve, you put the paddle wheel like that. I don't know if it's 4 or 5, that doesn't matter. And if you rotate like that, see this paddle wheel in the specific point rotate counterclockwise, the curve is positive. If the curve is negative, so the rotation is clockwise in the opposite direction. Okay, this is a famous hypothetic paddle wheel and rotate clockwise when the curve is negative. See, the curve is 0, is equal to 0, there's no rotation. No rotation. And this is important because the non-rotation vector field is the vector field that are irrotational, que is equivalent to say conservative vector field. And we study quickly, I probably will study more clear what is the idea for the conservative vector field. There's one fantastic way to determine if one vector field is conservative or not is compute the curve. See, when you compute the curve, the answer is 0. Entonces irrotational, no rotation, and the vector field is conservative. If it's conservative, remember, we can find a potential function to compute the work done in between 2 points. And not necessarily compute using another technique I want to explain, I don't know, see today or next class. Everything is clear about the operator. So let's see example. See, everything the theoretical part, the conceptual part, see, everything is clear. We are ready to using example. So see example. Okay, now example 1. Example 1, I like to start for the example 1. It was the same example that we analyzed last class. Okay, the vector field is radial. Vector field F in x comma y is equal x comma y. So I analyze quickly using the animation. No? In the last class, we see the animation today again. Okay, this vector field is total radial. So see, we are doing the sketch in the any point of the vector field. It's like that, radial. I expect in this case is irrotational, and this vector field is conservative. Okay, this is a P function, and it's a Q function, always PQ in 2 dimensions. In order to find divergence, okay, my formula is, this is my formula, look. My formula is partial derivative P with respect to X plus partial derivative Q with respect to Y. Partial derivative P with respect to X is 1. Partial derivative Y with respect to Y is 1. Y 1 plus 1 is 2. So that means that this vector field in any point, look at that, in any point, see the divergence is equal to get positive. So this point is source. Okay, and the interpretation is you make a zoom, you see a point, you see a small circle around the point. That means that the net float, so the flow in is smaller than the flow down. And make sense because it's radial and the magnitude of the vector increasing when the point is far to the origin, right? This is the interpretation. Okay. Entonces source. Es source. If you want to compute now the curve is the formula, that formula. Partial derivative q with respect to x minus partial derivative p with respect to y. Q is y, and partial derivative with respect to x is 0, minus p is x. Partial derivative with respect to y is 0. Y 0 minus 0 es 0. Entonces no rotate is conservative. Vector field. Okay, this is a fantastic way everyone in the world determines if one vector field is conservative or no. Compute the curve. Si the answer is 0, es conservative. So, si es conservative, es obvio que the potential function exists. Potential function exists. And the potential function we found, okay, in other words, what's the interpretation of this? The interpretation is that this vector field, this one, come from, for the computation for the gradient of the one function, que es scalar. This function is a scalar function. However, when you compute the gradient, we get this vector field. So my goal is backward. I have the vector field in my hand. I need to find the potential function where I come from this vector field. So it's similar to the antiderivative, but in this case, no antiderivative, anti-gradient. So we compute the anti-gradient, que es the antiderivative, pero component by component. It's no big deal. It's super easy to understand. For example, si you suppose, the supposition is that this vector field comes from, for the one function, que es gradient, it's because P is partial derivative P, partial derivative F, sorry, que es the function, with respect to X. And this is equal X in our specific example. So you want to compute the F. This is similar to the, the differential equation, no? This is a partial differential equation. Now you find the antiderivative. So you perform antiderivative P with respect to X. In our case, X is P is X, no? This is antiderivative X dx. And the answer is X squared divided by 2 plus something, but I don't care plus something. A plus, actually, in calculus 2, you put plus C, que es a constant, no? And this is a little bit more complicated because it's partial derivative. Because a partial derivative, actually, we have a function, no constant, sino a function que I want to call G of a function of Y, que es the opposite variable que your integration. So your integration, okay, let's do it backward. Suppose that I differentiate this. Derivative of this is 2x over 2. Derivative of this with respect to x is 0. Cancel out is x. I go back. Okay? But I don't care. It's not super important. I need to say that, but it's not super important to put this function. I want to explain why after. In order to find the second component of the potential function, well, okay, exactly, so you apply the antiderivative q with respect to y. Q is y, entonces y dy. Wow, entonces y squared over 2. And you put everything together. Entonces my potential function x comma y is equal to x squared over 2 plus y squared over 2. And the story. Suppose que I'm doing backward. Suppose I don't know this. Suppose I apply gradient of this function. Derivative the first derivative this with respect derivative this with respect x is equal 2x over 2 and derivative this with respect to x is 0. The answer is x exactly the same of our original vector field. Look at that. and partial derivative f with respect to y, differentiate that s0, and this is 2y over 2. Is y exactly the same as this. Okay, do you understand this? Okay, however, I have more. One more detail. Okay, this vector field, this potential function, sorry, look like, see, I try to do the graph of this. I've called x squared over 2 plus y squared over 2 potential function equals c. I put equals c because I consider a guy like a level curve. A level curve. Actually, it's not a level curve. It's a equipotential curve. Equipotential curve. It's a family. It's a family because it's C0 is a point, C1, C2, and so on, C3. And you remember, I suppose you remember, that the gradient is perpendicular to the level curve. So, for example, in one specific point, the gradient looks like that. It's perpendicular to the equipotential curve, which is similar to the level curve. In other point, for example, here, it's perpendicular. Okay, here it's perpendicular, but it's smaller, no? Because x is smaller now. But there are many ways, okay, to build the vector field, not necessarily using application. You can, well, CS conservative vector field. You determine the vector function, the potential function. Sorry, you are doing the graph of the potential function for several values of the C, and you determine in any point perpendicular the vector field graphic without sophisticated software. Okay, in GeoGebra or something. Do you understand the big picture? Okay, but wait a second. I want to show you an elegant animation. This idea. Let me see where. It's supposed to be over there. Over there. Let me share the screen with you of this. And by the way, I want to send this this application, no? It's GeoGebra. Okay, look. Okay, this is the vector field. I put X here, Y here. It's a PQ. P is X, Q is Y. Divergence is 2 at any point. And curve is 0. So no rotation, it's totally radial. Entonces you see, wow, look at that. Animation for the divergence is like that. Look. What means this flashing? This is like a Faust. And this is the water. Suppose to understand the thing, we suppose que vector field represent the velocity of the one liquid, water maybe, and this is a Faust. So any point is a Faust. Any point the net flow out is 2. So it's bigger than the flow in. And no rotation. In any point, no rotation because the curve is 0. This is totally irrotational vector field, and this vector field is conservative, and the potential function that you cannot see here in this animation is a family of the circle, concentric with the center, with the origin 0, 0, and any vector field in the point is totally perpendicular to the equipotential curve. Any question? Do you understand this or no? Confusing, very confusing, or very clear? Huh? Answer me. Yeah, clear. Okay, I understand. Okay, I bring 3 more examples. Entonces we investigate because we have in this moment the tools to investigate any vector field using the new operator that we studied, divergency and curve. Okay, divergency and curve. Suppose this vector field yx. And this is similar, but I interchange x and y. Now this is always p. P is the first, and q is the second, no? And we compare y now, divergency. I don't see the whiteboard. Okay, sorry. Okay, sorry. Okay, carajo. Okay. Okay. I say, okay, this is my second example. Number 2, no? And this is similar, very similar. The only thing I did was interchange x and y. And this changed a little bit this behavior. Suppose I compute divergence of f. Remember definition? Definition is partial derivative p with respect to x plus partial derivative q with respect to y. Okay, entonces now partial derivative p with respect to x is 0 plus partial derivative q with respect to y is 0. It's 0. Divergence is 0 in any point. Entonces this is called source free. No source in this vector field. Okay, what about the curve? The curve give me information about rotation. Definition is partial derivative q with respect to x minus partial derivative p with respect to y. Entonces es partial derivative q with respect to x es 1, ¿no? Es 1. Minus partial derivative p with respect to 1 is 1. Wow, 1 minus 1 is 0. Wow, entonces es again conservative. Si es conservative, entonces exists the potential function. Okay, because I try to find the potential function. Entonces, to find the potential function, we're using the anti-gradient. Anti-gradient is, you know, how I call that. It's the generalization of the antiderivative, but component by component. So you find the antiderivative in the p with respect to the x, and you find the antiderivative q with respect to y, no? Let's do it. Entonces, antiderivative p with respect to x is in our specific example is y dx. Si you antiderivative with respect to x, you consider y constant. Entonces es y outside and antiderivative dx is x. It's only x plus something. I don't care plus something. This is not important, guys. This is not important. Now, likewise, antiderivative q with respect to y is in our specific example, q is x dy. Similar idea, no? X is a constant, you put outside, antiderivative dy is y. Entonces, they are perfect coincidence. It's the same, no? The only thing is, but it's the same, no? It's a multiplication. Entonces, multiplication, you can change the order, right? And doesn't happen. Nothing happen. Now, the potential function f comma x comma y in this case is you take not both, you take only one. When they are repetition, it's obvious que es only one. Así es different, no. So you, in order to find, I promise that we see several examples of the potential function throughout this chapter. This is the elementary, the most kindergarten example I can find. What is the rule? The rule is clear. You find the antiderivative component by component, PQ. In 3D is PQR. But you find. Entonces, now you see, there are repetition, you take one time, no? See, those repetition, you collect everything. Every antiderivative and repetition, you take only one time. Interpretation this. Well, interpretation this. Graphic interpretation. We can interpretation this like an equipotential curve. Like a lever curve. This is a parabola. The parabola, no, sorry, the hyperbola. Like that. The other branch of the hyperbola, like that. You're supposed to get this is equal C, and C is equal 0, and C is 0 is nothing, C equal 1, C equal 2, C equal 3. In the other branch, it's exactly the same. C equal 1. Remember the hyperbola contains two branches. One in the first quadrant and one in the second quadrant. No? This is C equal 2. It's the same. And C equal 3. However, si C is negative, entonces we obtain another hyperbola, but in the third quadrant and in the fourth quadrant. This is, for example, C equal -1. This is C equal -1, and so on. C equal -2, -3. Okay, entonces how look like our vector field? Well, our vector field look like that. In any point, it's perpendicular. Look. In any point, it's perpendicular. Entonces, this is to get some roughly idea how look like the vector field, no? The magnitude, one of the magnitude, you need to compute it with the original expression, no? But that's easy. Okay, so this vector field look like that. It's obvious because you go far to the origin, the magnitude is bigger, no? Makes sense, right? Because the vector field, the component is y and x. So far to the origin is 0, 0. I suppose that this vector field is bigger than this, no? Super. Let me see. So divergence 0 and curve 0. No rotation and no source. Wow. It's weird, this vector field. Let me see in the animation. Okay, the animation I have here. Okay, I promise I send the link to connect it with this animation and you practice by yourself. This is funny. I don't know, at least for me it's funny. Okay, let me see. Okay. This is the last example again, no? However, in the new example, I changed something. Look, I put here. No. I put a y here. I change y. Yeah, x. Yeah, mark here. This is the idea for this vector field. You see, in any point, divergence is 0, no source. Wow. And no rotation. Wow. In any point, you drag this paddle wheel and no rotation. And you see here clear, divergence is 0, curve 0. Any question? That was example 2. No problem. Moving on to the whiteboard. I want to share whiteboard now. I suppose you see whiteboard, right? Let's move on to example 3. Everyone follow me? Everyone follow me, guys. Do you understand very well the idea? This is a little bit complicated, abstract. But little by little, you'll be familiar, no? Example 3. Example 3 is another vector field. I bring 5 examples. Case is -y, x. Okay, I have no idea. I compute the divergence. By definition, I copy always the formula, no? Px plus qy. Derivative p, this is p, and this is q in our example. Derivative p with respect to x is 0, non-depending of x. And derivative q with respect to y is 0. This is 0. Again, what happened is source free. Vector field, no source. Okay, curve. Well, a curve is definition, the formula is qx minus py. Okay. Derivative q with respect to f1. Okay, good. I like that. Minus derivative P with respect to what is negative 1. Double negative becomes positive. 1 plus 1 is 2. Entonces this vector field rotate counterclockwise. So rotate, rotation, counterclockwise. When you see the animation, you see that the paddle wheel is moving in this direction. Entonces this vector field, of course, no conservative. Conservative. Therefore, then we have no potential function. So the potential function is only privilege of the conservative vector field. By the way, the majority of the vector field is non-conservative. So conservative is special category of the vector field. Okay, it's okay. I finished because I cannot do anything more. Suppose example, no. See, yes, of course I can see the simulation. Okay, let's do an example 4 and you see 3 and 4 together. Because it's similar, very, very similar. Look at that. The vector field in this case is y, comma minus x. It's similar. The only thing I did was change the sign here. So using the common sense, well, I have no idea, but I suppose que rotate, no? Pero rotate in opposite direction. I don't know. Let me try to compute the divergence and curve. So divergence is definition px plus qy. This is p, this is q in our vector field right now. Derivative with respect to x is 0 plus derivative with respect to 0, again is 0, and we get the same conclusion, source free. No source in any point of this vector field. However, let's see what happened with the curve. The curve operator is qx minus py. The partial derivative with respect to the x of q is -1 minus, definition half a minus, subtraction, and partial derivative with respect to yp is 1, positive 1, entonces -2. Entonces -2, the rotation of this vector field is clockwise. Like that. Entonces again, when the curve is not 0, see the curve is not 0, entonces it's non-conservative, then we have no potential function. So the fantastic way to determine if one vector field is conservative or no is compute the curve. So the curve is 0, conservative, and we can find the potential function using anti-gradient operator. However, see the vector field is the curve, of the vector field is a number, positive. Entonces our vector field rotate counterclockwise, otherwise, si es negative, rotate clockwise. Let's see the animation for both vector field. Okay. Animation here. Okay, here, I suppose here. Okay, share the screen. Okay. Here, over there. Okay, there you go. Do you see the simulation? In the first example, here is minus y. Okay, I put it minus y. X. Okay, good, very good. You click here. Okay, look at that. This vector field, the divergence is 0, so source free in any point. You move this, source free, okay. However, in any point here, the curve is equal to, regardless the point you select. And you can see how the paddle wheeling spin counterclockwise. exactly like the arrow of the vector field indicate. Like a hurricane, que rotate control go Y always. Now, see, I change, for example, 4. I change a little bit. Example 4 is negative x, no y. So I change a little bit. It's a y now positive, and this is negative x. Negative x. I press enter. Oh, a similar idea. A similar idea. Divergence 0. Look at that. However, the curve is negative 2. Any point here, the vector field rotate clockwise. Negative is clockwise. Positive is counterclockwise. Any question? Any question? Any question? What part you don't understand? Operator, vector field. Okay, let's move on. Whiteboard. Whiteboard now. Okay. Do you see whiteboard? Good. Let's do it by curiosity. One more example. Little bit, weird, complicated. Suppose vector field like that. This is example 5. It's the last one of this part. In 2-dimension, because I want to explain now 3-dimension. In 2-dimension is this vector field que is 0, minus absolute value x plus 4 over 4. And one more time, we compute divergency. Divergency of the vector field, que by definition is px plus qy. And we compute also, why not, the curve of the vector field. It's just a formula, que is qx minus py. Okay, now this is p. So p in our vector field is 0, and q in our vector field is this complicated, not complicated, but weird formula que involves somehow absolute value. So p, so you want to do the divergence first. You define the derivative, partial derivative p with respect to x is 0, and partial derivative q with respect to es 0, es 0. Entonces, es 0, entonces source free, this vector field. Entonces, now in this case, a little bit more complicated. Q with respect to x. Entonces, now in order to find, look, this expression is minus absolute value x over 4. So you split this common denominator plus 1, no? Because 4 over 4 is 1. So you differentiate that. Es obvio que derivative 1 is 0 and 1 over 4 is a constant, so I put outside the gain, minus. Yeah, I focus in the derivative absolute value. Okay, this is a little bit weird. Absolute value, remember, let me try to explain. This is calculus 1. Absolute value function look like that. This is absolute value function. I know that the derivative is the slope of the tangent line. Okay, so I try to do the graph of the derivative absolute value. I see in the first quadrant the slope is 1, positive 1, because this is oh, okay. Another way to see absolute value is x if x is positive, and minus x if the interpretation this is positive and this is negative 1. You see, if you differentiate that with derivative x is 1 if x is positive, and derivative this is negative 1 if x is negative. Wow. And this function receives one particular name in mathematics, it's called a sign. the negative 1 over 4 sine x. Es, you know, it's a name. Okay, this is the sine function. It's a function que es negative, a positive 1 for any positive number, and it's negative 1 for any negative number. Okay, and this is okay. So now our curve is negative 1/4 sine of x minus, and the p with respect to y is 0. So it's nothing. It's nothing. And this is the, because you can see that one vector field, not necessarily the curve is always positive or always negative, depending. In this case, it's both, depending on the region. Let me show you the animation to visualize this idea. Look at that. Okay. 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 I suppose in this moment you see the animation, yes or no? With the previous example. Now I select one example here. You have pulse A. Let me see. Pulse A. I press here. Done. Hey, what's going on? Yeah, I understand. We need to cancel that. Okay. Okay. Look. Okay, this is the vector field, que es 0 and absolute value minus absolute value x plus 4 divided by 4. The divergence is 0. And the curve is this expression, que es, you know, minus the sine function. This is the sine function. The divergence is 0 in any point. Source free. However, look at that what happened. In this case, when the x is positive, when the x is negative, in this case, both paddle will rotate counterclockwise. However, so I move this to the other side. Now this rotate clockwise because it's positive, no? This is positive x. Look in this formula. Entonces, however, si es minus, es opposite sign. So in this case, look, the curve is positive. Si es positive, rotate the vector field counterclockwise. Si es negative, rotate the vector field clockwise. Wow, fantastic. I like that. Any question? Any questions? You have no question? Well, entonces I go to the 3-dimension. 3-dimension. 3-dimension now. I go 3-dimension. Because everything that we study, the formulas that we study, is only valid for 2-dimension. In 3-dimension, it's a little bit more complicated as always, no? When you increasing the dimension for the problem, always the problem is more complicated. Now compute the same operator. We compute the same operator, divergent and curve, but in 3D. So in 3D, our vector field is x, y, z. And the vector field contains 3 functions that normally we call it PQR, 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 PQR. P, of course, is a function that depending of, okay, P is a function that, of course, depending x, y, and z. Like y, q depending x, y, and z. In general, no? And r depending x, y, and z. So the definition for divergent in 3D is exactly the same. Divergent in 3D is partial the p with respect to x plus partial the q with respect to y plus partial the r with respect to z. End the story. Super easy, super easy, super easy. However, the curve no, it's complicated. The curve is a little bit more complicated. So no, number one thing different in 3D. Okay, the curve now is a vector. Okay, divergent no vector. This is a scalar function. Always, divergence is scalar. And in 2D, divergent and curve both are scalar. However, in 3D, no. In 3D, the curve is a vector. Yeah, I want to explain the interpretation for the curve No. And the formula is a little bit complicated. It's r partial the r with respect to y minus partial the q with respect to c, comma. This is my first component. Pz minus rx, comma, and qx minus py. Entonces, nobody remember this stupid thing. Entonces, the mnemonic device to remember is a cross product. Okay. Cross product. It's similar to the cross product. Entonces, now pay attention. Pay attention now. This very, very, very nice and convenience notation to represent divergency anchor in 3D. Okay, look. We define this operator, que normally is called del. Some book call it nabla. They're the same. This is totally hypothetical. It's partial, it's a vector. Sorry, it's a vector. It's a vector. And the component for the vector is partial with respect to x, comma, partial with respect to y, comma, partial with respect to z. And you see, bueno, professor, pero partial of what? We have nothing here. No, because it's totally hypothetical. Okay, it's the mnemonic device to remember the formulas. Entonces now, instead of you call divergence f, you put nabla vector dot product f. Entonces, who is nabla? Bueno, nabla is the vector que is partial with respect to x, comma, partial with respect to y, comma, partial with respect to z, dot product, and the vector f is PQR, no? PQR. And when you perform the dot product, when we have partial derivative p with respect to x, que is this times this. This is totally symbolic. Es like a mnemonic device to remember the formulas using the convention that we are studying in vector calculus. In vector calculus, no, in vector in general. Entonces, this is dot product, and this is plus partial derivative q with respect to y, plus partial derivative r with respect to z. Well, this is no big deal, because these do not apport any extra information. It's the same thing of this, right? It's present in different notation, but it's clear. However, in the curve, it's important, because in the curve, this expression is very, very weird. I never memorized. This is stupid. However, si you call delta cross product f, and you perform, I promise that we are doing this operation 1,000 times from now, I, J, K. Look, it's weird. You put it here, partial derivative nothing with respect to x, partial derivative nothing with respect to y, partial derivative nothing with respect to z, and you put here PQR. And you solve this determinant. The first component is high. Entonces, in high component, we have, look, you delete mentally this and this. Entonces, we have partial derivative r with respect to y, que is exactly this idea. Okay, ry minus partial derivative q with respect to c. Do you see it's fantastic, this notation? Minus j. Now you delete this, and you have that and that. It's partial derivative p with respect to z. Oh, no. R, sorry, with respect to x, minus p with respect to z. So you see, well, no, professor, this failed, because here is pz minus rx. No, remember, we have minus here. Okay? Plus k. And k, we delete that and this. And we have partial derivative q with respect to x minus partial derivative q p, sorry, p with respect to y. But close the parenthesis. Sorry, it's a parenthesis. Sorry, is the parenthesis. And if you want to express this like a vector, it's exactly like this. Do you see that? By the way, curiosity. Curiosity. The last part is this. It's the formula qx minus py. It's the formula for the curve in 2D. Entonces, the curve in 3D is a vector. And the interpretation of this vector is in one specific point in 3D, we have rotation, suppose in this direction, and this vector is perpendicular to this. Okay, this is a curve of the vector field in one specific point. And the magnitude, this vector represents the angular speed of this. And similar idea, si es counterclockwise, is when the curve is positive, and a positive curve, and clockwise is negative. And 0, no vector, is no rotation, and this is conservative field in 3D. It's exactly the same. Entonces es important, guys, que you understand the new notation using del. This is fantastic. We use it throughout this moment. So when I write something like that, del dot f, this is equivalent. No, you use a vector if you want diverge. Now you see del cross f is curve. And the interpretation is the diverging is exactly the same. Source sink or no, or source free when it's 0. And the curve now, the new thing is a new formula, more complicated, of course. And also, it's a vector. So the answer is a vector. Okay? Let me try to do at least one example, because after that we are doing some problem of this. One example of the curve and divergence, in 3D. Any questions so far? Do you understand the notation? Do you understand the new notation using del operator? Del operator is like a mnemonic device. It's like a symbolic language that we're using in vector calculus. Everyone using this language to call divergence and curve in 3D. Okay, let's see one example in 3D. One vector field is given. Okay, no problem. Vector field is given in 3D. X, Y, Z. Is, y squared c cubic, comma, 2xy c cubic, comma, 3xy squared c squared. I might go, why not? Let's compute everything, the divergency and curve. Let's start for divergency, que always is easier. Divergence. No. Let me try to practice a little bit the new notation. Compute that. Compute that. Compute now del dot f. And you need to understand, when they write in that way, it's diverge. It's equivalent to say diverge. Entonces the formula is when you have P, this is PQR. Look at that. P is this formula, this expression, expression. And you partial derivative P with respect to x plus partial derivative Q with respect to y plus partial derivative R with respect to Z. Okay, partial derivative P with respect to x is 0 because we have no x, plus partial derivative Q with respect to y, well, we have only one y, and derivative y with respect to 1 is 1, and you consider that the rest is a constant, entonces 2x c cubic. plus partial derivative with respect to z, entonces we have one z here, pero it's square, entonces 6 times xy squared c. This is the expression. Let me copy elegant. 2x c cubic plus 6xy squared c. End the story. This is divergence of this vector field. Bueno, entonces in this case, you know, it's a variable. Entonces now, when you evaluate in different point, que you consider that you need to understand x, y, z, you plug in the value for the x, y, z. Si es positive, is source. Si es negative, is free, sink. And si es zero, is source free in this specific point. Okay, no in general. Now let's move on to the curve, que es complicated, more complicated. It's to compute the del cross f. Okay, so I found, look at that, ijk. I copy derivative with respect to x, derivative with respect to y, derivative with respect to z. And you copy the expression PQR, que es y squared c cubic, 2xy c cubic, and 3 times xy squared c squared. Boom. That's it. Okay, let's do it. I propose the following organization. Put 3 different rows. One row for the I is like that, bang, bang, bang. Because I have here inside parentheses, and you perform partial derivative, this expression, que es R, with respect to Y, entonces es 6 what? 6x y c squared. And you differentiate this and this in the determinant, right? With respect to y, entonces 6x, 1x, 1y now, because the point is decreasing, and c squared stays the same. Minus, and now the derivative in this direction, que es negative. Okay, entonces derivative with respect to z is again 6xy c squared. Because these 3 go to the front, multiply by 2 is 6, xy stay the same, and the exponent of the c decreasing by 1, entonces 0. Okay, entonces 0 is 0i. We have no component. Okay, it's possible, no? Minus j, and now you delete mentally this column and this row, and we compute this partial derivative and this partial derivative. Partial derivative with respect to x is 3y, 3y squared c squared. Because we have only one x, and partial derivative x with respect to x is 1, and the rest you consider like a constant. Minus, and now partial derivative with respect to c is 3y squared c squared. Well, in this case, no. In this case, we have 3 cubic, no? C cubic, and this is 3 go to the front 3 and decreasing by 2. Again, it's 0j. You know, it's no minus, it's 0j, because 0 have no sign. Okay, now finally k positive in this case. You delete mentally this and this, and focus on this. This is partial derivative. This is 2yc cubic, because we have only one x. And derivative this with respect to y is minus 2yc cubic. Again is 0k. Therefore, the answer for the curve is the vector 0, 0,0. In other words, you can indicate like a 0 vector, null vector. Si es null vector, entonces this is no rotation, no rotational. This vector field is conservative. And we are ready to find the potential function. Do you understand the procedure? The procedure is super easy. It's exactly the same we are doing in the numerical vector, but now it's the vector calculus, you know, vector functions, PQR. No, see, the answer is no 0, entonces no conservative vector field, therefore stop. We cannot do any more addition. So remember, and I know, see, the answer of the curve is zero vector. It's because this vector field is conservative. Si es conservative, exists the potential function. Entonces, what is the procedure for finding the potential function? Bueno, compute the anti-gradient, que es compute the antiderivative component by component. Let's do it. Okay, for example, you take, for example, integral antiderivative p dx. You compute the antiderivative q dy. You compute the antiderivative r dz. And after, when you find this expression, and this expression put together without repetition, when it's repeated, not necessarily included. Entonces now, integral y squared c cubic dx. This expression do not depend of x, entonces es a constant. You can say, entonces es, si you put in alphabetic order, no, it's x y squared c cubed. I know that we have plus something, but I don't care plus something. Integral now 2x y c cubic dy. Well, entonces you integration with respect to y, the rest you consider a constant. And this is y squared over 2, no? And these two is cancelled. And you organize in alphabetical order, you have x, y squared, c cubed. Wow, it's a coincidence, que it's the same. And you take no 2 times, you take only 1 time. Okay, now finally the last component, que is r, que r is 3xy squared, c squared, dz. New integration now with respect to z. You consider the rest, que no depending of c is a constant, you put outside. And we focus in this integral, no? And this integral is c cubic over 3, and the 3 is cancelled, and you organize in alphabetic order, and we have x equal x y squared c cubed. Wow, amazing, it's the same. Not always happen, guys. You see, I promise you see several examples of this. So my potential function, little f is the notation that we use for the potential function, and capital F is the vector field notation, and this is scalar. Entonces, comma y comma z is equal x y cubic c square c cube. This is my potential function. I promise the next time we're using every day the potential function. Any question? Any question? Do you understand this? 3D and 2D? Okay, to finish that, we have time. Super. I like to have time. Don't rush. Okay, I want to hear opinion. Everything is clear, everything is confusing. A ver, Leonardo, Carlos Luca, I need to talk to you. When the class is over, please stay with me, okay? No, don't be scared. It's one thing. Omar, Brandon, a ver, another guy, Fiddy, Victoria, Daniela, Giraldo, you say something? You understand or you don't understand, Giraldo? David Restrepo and Shagir. Okay, understand. Okay. It's no big deal. Okay, let's move on again to the whiteboard. Let me erase the whiteboard. I want to prove. So this is okay. This is the last part, in which you manipulate a little bit the operator. No, okay. I want to prove this identity. Suppose they want to prove the curve of the gradient of the one function, scalar function, is equal to 0. In 3D, entonces si es a curve, we ending in 0 vector. See, we're using another notation, the convenience notation, using delta. Remember? Bueno, this is delta multiplication, f. This is no dot product. This is just multiplication. Remember the definition of the gradient is partial derivative of x, comma, bueno, with respect to x, comma, partial derivative f with respect to y, and partial derivative f with respect to z. And this is a vector, because the gradient is a vector. Okay? Entonces now, well, si you have nabla, que nabla is this hypothetical vector, if you multiply by the function f, que es scalar, so you put it here, you put it here, and you put it here. No dot product. No dot product. Entonces, si es dot product, es divergence. Ajá. Entonces, dot product, you indicate like that. So this is divergent. Of course, it's a vector field, no function. This is gradient. And the gradient, f is little f. And this is the curve. This is the curve in 3D. Okay. And finally, I apply to this a curve. So I want to prove this. Okay, let's practice. This is a practice a little bit. So in order to do the order of operation, you start for the operation inside the parentheses. Entonces, si you compute the gradient of the function f, it's obvious que es partial derivative with respect to x, comma, partial derivative with respect to y, comma, partial derivative with respect to z. It's exactly the same of this. This is the same. And now I need to compute another operator que es a curve. Okay? A curve in 3D, you know, is doing using the determinant, ijk. And you put a symbolic del here. Now here you put f of x, f of y, and f of z. It was the answer for the first operator, that was the gradient. Okay, let's do it. Entonces, I is, look at that. You delete mentally this and this. We focus in that part. A partial derivative. So partial derivative f I did before with respect to z, and now with respect to y in the second loop. Minus, now partial derivative y I did first with respect to z, that's yc. Do you see that? Okay. I did the first derivative using the gradient. No? Now I'm using the curve. I compute the second derivative. That is the reason that we have different letters. And remember, f, for example, cy is equivalent to, say, partial derivative f with the z first and y secondly. This I did before. Look here. Now I compute the partial derivative. And by the way, the cross it, so the f cy is equal to f yz. I prove this in one moment, that this is 0. Minus j. Entonces I compute mentally this and this is partial derivative z x minus partial derivative xc. Again is 0. Wow. Bloqueé. Entonces es, okay, es the partial derivative yx minus partial derivative xy. Okay, it's also 0, and this is 0 vector. I prove that. And making sense because the gradient, okay, remember gradient vector field is conservative. No? So using the common sense, a gradient vector field. So you have a function f, a scalar. When you compute the gradient, you obtain a new vector field. If for sure this new vector field is conservative. Si confront of the one potential function f. Entonces, when you compute the curve, it's obvious que es zero because it's conservative. This is one identity. Do you understand this? This is just illustrate manipulation of the operator guy. Okay, maybe in electromagnetism and fluid mechanics, the professor explained this subject using this identity, and you need to understand the meaning. So the formulas, but the most important, what the interpretation of this, because it's the way to manipulate vector field. Okay, I want to prove another identity. Proof. Okay, it's divergency of the curve of the vector field using the another notation, using del notation. This is dot product because of divergency, parenthesis, del cross f. I remember f is vector field in 3D PQR. According to the order of operation, the first operation we should do is the curve. And the curve in 3D we compute using the determinant. Partial the x, partial the y, partial the z, and we have PQR. Okay, so we have, well, in this case, look, the first is the first component. Okay, sorry. The first component, vector field here, vector, and the I is R Y using this notation, guy, minus QC, comma, and J is chan like that. Entonces es partial this, que es Rx, minus Rx minus PZ. But remember, in J you need to change the sign. It's minus J, entonces es PZ minus Rx. Okay, good. Okay, and now finally the third component is, when you delete this and this is Qx minus Py, no? Py. Okay, super. Yeah, I need to find now. Let me erase that part. Okay, that part erase. I need to find now divergence. And divergence by definition is derivative dot part with respect to x, derivative dot part with respect to y, and derivative dot part with respect to z. So we have, so you differentiate this with respect to x. So remember the formula for the divergence. Let me copy here in one corner of the paper. Is px plus qy plus rc. But this is my p now. So don't confuse it with this. This is my big P. PQ and BR. Now U differentiation. So U differentiation in the order is RYX minus QCX. I did that part. Plus PCY minus RXY. Plus derivative R with respect to C is Q XC minus PYZ. Wow, look at that. This is cancelled with this. This is cancelled with this. And this is cancelled with this. Because the order of differentiation is not important. And this, the answer is 0. But this 0 no is not 0 vector. No. It's 0 scalar. because divergent give me information on the scalar. So this result is totally source free. Do you understand this or no? Confusing, very confusing, or very, very clear? We have 10 minutes. In 10 minutes, clear, operator, fantastic, give me information locally in one specific point, what's going on with the vector field, okay? Now, we studied new thing, well, at least to start a little bit, new thing, que es line integral. Wow, what the hell is that? Line integral. Guys, I promise that when this chapter is over, I want to dedicate some minutes to explain the big picture about integral. Because we studied double integral, we studied triple integral, and we studied a new one, it's called a line integral, I want to explain right now. The definition, maybe we have no time to do several examples, at least one. This is a line integral. And that's it, no, we continue another integral, surprise. Okay, remember, integral is a Riemann sum. A Riemann sum. What is the idea? What is the definition of the line integral? Suppose we have in 2D, we have x and y. And we have, why not, a curve. It's important, guys, the orientation. The orientation. Entonces, I need to define one integral. You need to be familiar with this new notation. Integral over the curve C, similar to the range of the C curve of the function in 2D, ds. And who is ds? Who is ds? Okay, for example, you can remember the Riemann sum. Riemann sum is, we have a function in 2D or in 3D. We have a region. In this case, is in the ambiental is 2D. However, the object is 1D because it's a curve. And you split, you chop this line in different pieces. And this piece is my famous ds. It look like R length, no? This is ds. Okay, now, see, I say, what is the definition of the line integral? Well, the line integral is the same thing, a Riemann sum, but it's a Riemann sum in this direction. Look at that. You find the limited, always the limited. When it's something I don't know, the summation, Riemann sum. Entonces you take the function, and you evaluate, for example, here, in one piece, you evaluate in one arbitrary point, que normally I call x after, comma y after, and this indicate after it because it's totally crazy arbitrary point in between ds, the infinitesimal segment, que actually you can consider like a segment. Actually, it's no segment, it's a curve. Multiplication by ds. And you adding different pieces. Let me indicate like that, pieces. Okay, this is different pieces, 1, 2, 3, 4, 5 pieces, and you consider that ds approaches to 0. Okay, this is the idea. Now, suppose to understand more clear. What is the interpretation? What is the interpretation, professor? Remember, the interpretation for the integral depends on the nature of the function. Suppose that this function represents the density. Density function of the one wire que represented by this curve. Actually, the name is line integral, but it's not a line integral, it's a curve integral. Entonces, this is the density, multiplication by the ds, que in my opinion, ds is like R length, infinitesimal R length. represent the answer of this represent the mass of this wire in one specific interval. Okay, entonces this is the mass. Interpretation is a mass of wire in one specific interval. When pero I have more. Suppose que the function is 1. Remember, when it's 1, change completely the dimension. Entonces, when it's 1, entonces we can find, si the density function is 1, entonces we have 1 ds. Bueno, entonces stay the same idea as the mass of the wire, but under the supposition que the density is constant, es 1, is unit. Entonces, this is the R length. Okay, the line integral become like the integral that we studied in calculus 2 of the R length. Okay? Do you understand the idea a little bit or confusing a little bit? This is no big deal. This is no big deal, but you need to tell you brain to the new situation. It's vector calculus. Look. How you solving that? Well, you solving easy. You are doing the parametrization of the curve. Okay, parametrization of the curve. To compute the line integral, you are doing parametrization. To compute line integral, we are doing the parametrization, parametrize C, o sea, parametrize the curve. Y I suppose que the parameterization is two new functions que I want to call x of t and y of t. And don't forget, when you parameterize something, define the interval. Without interval, you are doing wrong. Put the equation right and the no interval specification, so you are doing nothing. Basically, you can interpretation the parameterization like a substitution. Okay, you convert one object que es one dimension, pero living in two dimension context, two dimension ambiental, and one dimension que es A to B. So this is T. This line is T, A to B. This is I change this to this. I suppose hypothetical get the point A here and the point B here. So we are doing the line integral in this portion. You are doing the parametrization like that. You can interpretation this like a substitution. Okay, substitution. Now substitution how? Well, substitution in this way. Look at that. Look at that. The line integral and the curve C. Okay, x comma y ds is equal. Well, entonces I convert magically the line integral in one common integral que we study in Cal 1 using the parametrization from A to B, and you replace x is x like a function of t, y is a y as a function of t, and ds is a square root dx dt square plus dy dt square dt. And this guy es obvio que es 10, que es the R length, the infinitesimal R length, this one. When you chop this, split infinitesimal R length. And this formula is no surprise. You see before in calculus 2. Okay? But this is in 2D. In 3D, it's a little bit different. Okay, entonces we have time. No, we have no time to do one example, coño. Okay, no problema. Okay, I understand now. Okay, now. Okay. Let me see your face now. Okay. Okay, guys. Okay, let me stop sharing. You see my face? Okay. Okay, look. Entonces, Duque, please stay 1 minute. I want to go to drink some water. I'll right back. The rest, the student can leave. Okay, today I want to. Okay, thank you. I don't know. I cannot stop the recording. Okay. Somebody have help me to stop recording because in my mouse I cannot record it.